And that's the heart of the algorithm. So here, you are doing this operation n times, and just let's let d be 2. So we're working on triangles. So if you do this n times, that would be an n squared operation that you do n times. So this is n cubed. And then if you look at this operation, this is sparse, and so it's order n. And you're doing it n squared times because it's in a doubly nested loop. So this is also n cubed. Okay, so there's a sketch of the complexity count that shows that, if m and n are approximately the same, that this is n cubed rather than n to the 4th, which you would get by the naive matrix vector algorithm. Okay, it turns out, in general, you get, I think I have the parenthesis in the wrong place, but you get the dimension of the polynomial space to the 1 over 1 plus d rather than n squared. Okay. So this actually is, if you've done any spectral element methods, is the same complexity as doing a rectangle and just doing things dimension by dimension with tensor products. Okay. You had to work a little harder to get it, but it's true. Okay, now it turns out once you've done the stiffness, once you've done the mass matrix, the stiffness matrix is almost as easy. Okay, and that's because we can do a certain factorization of the stiffness matrix into derivative matrices and mass matrices. Apply your result for mass matrix, derivative matrix is sparse, so you're done. Okay, so here's the stiffness matrix. So what I'll do is really observe that it's D matrices. I take the gradients, I express them in terms of the Cartesian coordinates, pull the sum out, and so now I have K over SD M N I. So the I is just the chunk of the stiffness matrix in the ith Cartesian direction. Okay. So now I'll look at one of these matrices, and so A. So this is just the mass inner product, the L2 inner product, acting on some derivatives. Well, I can express these as just being the derivative matrix times the mass matrix. It's and so it's easy to come up with this factorization. So once you know how to apply the mass matrix, this is sparse. So apply it. Apply the mass matrix with a fancy, with the fancy algorithm. Then apply the transpose of the derivative matrix, and there's your fast algorithm for stiffness matrices. Okay, and so it's about d times the cost of applying a mass matrix. Okay, so I did some numerical experiments with this. I started out trying to do it in Python, but I kept asking for features that hadn't been wrapped into the PyDolphin interface yet. So I finally broke down and used the C++ interface, which was probably better for timing results anyway. And then I used the abstract linear algebra interface. I provided some helper routines for barycentric coordinates, Bernstein operators. So I used the paradigm scatter, apply the fast matrix, and then gather the result. And I did all the results on my Mac laptop. So I just did the 2D thing, but here's increasing polynomial degree, and here's the dimension of the local polynomial space. Here's the time, I forget, maybe 128 by 128 mesh. I just used the unit square and meshed it. Here's the time for doing the mass matrix. I didn't put in a plot, but if you do a least squares fit to this, you get about, that it's order into the 3 halves, which is what you expect. And here's the time for the stiffness matrix. Now notice that the stiffness matrix actually is only asymptotically about twice as expensive as the mass matrix. That's because there's a bit of work in scattering the degrees of freedom and gathering the result. The cost for the scatter-gather operation is the same for mass and stiffness because you're acting on the same local degrees of freedom, and and so that's an order n process, and so so you have to let n get large before before the computation cost is catching up over the communication. Okay, so some other comments. So it turns out I didn't do a very optimized approach on this, but if you actually build the global stiffness and mass matrices, they're actually still a little faster to do the matvec than my matrix free, but they take a lot more memory. But asymptotically, for higher order, my cost is actually approaching the Dolphin matvec. And it's also much, much cheaper because you spend 10, 20 times the cost of a matvec to build the matrix, and then you have to start applying it. Okay, so some conclusions. So it turns out that some standard operations on the simplex for finite elements I can make spectral, or spectrally efficient, using these special structures I found for Bernstein polynomials. Okay, so I think there are some possibilities here for the exterior calculus bases that Arnold, Falk, and Winter have worked with. Obviously, for their zero form bases, I've done that. But they are able to derive things for h-curl and h-div for their 1 and 2 forms in terms of barycentric coordinates. It may be possible to relate those bases back to the Bernstein polynomials, and if that can be done efficiently, then my techniques would carry through for h-div and h-curl. Now, the problem is straight sides constant coefficients only take you so far, as we found in our work on FFC. I'm investigating using this degree elevation technique to make quadrature happen. There's some preliminary things that maybe I can talk about another time. But also here, higher dimensional problems. Notice that my operation count was good in terms of the polynomial degree as you increase the dimension. So if you had a 4D or 5D mesh, these might be interesting algorithms to try if you want to do simplicities. And so so I've passed on a draft of my paper on this to Peter, and so he has some interest in doing some high dimensional quantum mechanic calculations with it. Okay, so I think I'll stop there.